Hello, everyone. Hopefully you can see my slide. So thank you for, okay, good. Thank you for joining me, our 27th C++ meetup, San Diego C++ meetup. We have a very special guest. I'll introduce him in a moment. Just want to mention that the meetup fees are paid and sponsored by Qualcomm, the wireless research department. So thank you, Qualcomm, for sponsoring this event. The agenda for today is, as I mentioned, we're hosting Andreas Fertig, and he would be talking about C++ templates. So let me introduce him. Usually we have other things. Today it's going to be Andreas talk. And of course, the regular stuff, if you want to have a talk in the meetup and all, just approach me, I can help. And there's lots of topics that we can come up with. So without further ado, let me just introduce Andreas. So Andreas Fertig is the CEO of Unique Code. Is an experienced trainer and lecturer for C++ for the standards from 11 all the way to 20. Andreas is involved in the C++ standardization committee in which the new standards are developed. At international conferences, he presents how code can be written better. And I like this sentence. I also want to learn how to code better. He publishes specialist articles, example for IX magazines, and has published several textbooks on C++. I have a couple of the published books from LeanPub on the left-hand side, as you can see here. With C++ Insight, CPP Insights.io, Andreas has created an internationally recognized tool that enables users to look behind the scenes of C++ and thus to understand constructs even better. This is one of my top favorite websites in the entire World Wide Web. People know that when I have my weekly Wednesdays in Qualcomm, we have a weekly noon, usually in Wednesday, where I kind of introduce all kinds of C++ topics, and we use this tool quite a lot. And I show people how actually what a compiler is actually seeing under the hood, which is a very, very useful tool for learning what's happening and teaching and all. So first of all, thank you for creating this tool. This is an amazing tool. Before working as a trainer and consultant, he worked for Philips Medizin Systems for 10 years as a C++ software developer and architect focusing on embedded systems. He has a website that I encourage people to take a look at later, andreasfertig.info. And also I mentioned, at least for my knowledge, I know about 2 books that I proudly own from leanpub.com. And these are the links and these are the books I highly recommend people. And I think we had at least one, maybe even both of them in one of the monthly book recommendation in the past few months. That's it from my side. I'll stop sharing and have Andreas take over. So we have people, we have 22 people and people trickling in. Thank you everyone spending your time with us on Saturday.
All right. Thank you very much, Kobe, for this very lovely introduction. Thanks for having me. There is not much left to say about me. It's practically my whole bio. Today, I like to talk about C++ and templates because I think they are one tremendously great feature about C++. We can do an awful lot of things with them. But I also know that some people are sometimes scared away by them. So I have colleagues, they say when they see the ankle brackets, they practically don't touch this code. And I somehow also made it my mission to reduce this number of people. You should at least be able to understand them and maybe also go there and write your own templates, because even small templates can help you very much improve your code base and so on. So this will be the topic of today. Let's make this interactive if you like. So because it's not a conference talk, I'm not limited to 60 minutes. I planned 1.5 hours for this, but I'm happy to take questions, and if it takes a little bit longer or so, that's totally fine with me. Kobe also introduced C++ Insights already. We will use this tool to peek behind the scenes of certain constructs at a time, and we can go deeper or less deep depending on what you like. So feel free to raise questions, to ask me anything you like around this topic, and stop me at any moment. Okay, that's totally fine. There's one thing I usually introduce. This is my last name. My last name is Fertig. And in Germany, or in German, that's an adjective, and you can translate it roughly as finished, ready, complete, or completed, which is a really great last name. You can make an awful lot of jokes about this because it makes always people smile if you tell them that you're already fertig. And over the time, it helped me to learn that certain people in the C++ community also speak or at least can read German, so Herbsata, Piano, Sturstub, and so this is also always a mind opener. And when sometimes it gets me also confused. I remember a trip where I went to CPP on C, probably 2019, and I arrived very late at the hotel, and I was very tired given that. And when I was checking in, I had a little chat with the receptionist, and at some point he asked me, Finnish. And I said, no, I'm German. And he said, no, Finnish. And I was, no, I'm German. Oh, no, I got it. He understood my last name and I didn't, because he lived for some time in Germany. And so he was able to get it and translated it into English. But at the moment, I didn't realize that one. Anyway, what is generic programming? Generic programming is a method to implement algorithms and data structures in most general, sensible way. Algorithms are written in terms of types to be specified later. This is the goal of templates, if you like. So we are not thinking about the actual values, but about the algorithm and maybe about which types can this algorithm used with later. The term generic programming itself was originally coined by David Muser and Alexander Stefanov. They did a lot of work, or at least Alexander Stefanov did a lot of work there, bringing us the STL as we know it as of today. Without him, we probably would not have that tremendously helpful thing there. Generic programming helps us, and that's the key here, to reduce redundancy and programming effort while it increases usability and flexibility. So this is what I started with, and this is why I like templates so much. In the end, templates generate code. If I instantiate any template with 2 different types, then I will get 2 different instantiations for these types. We will see that later. So it's twice the code as opposed to instantiating it only with 1 type. But it's the same as we would do it if we copy and paste it ourselves and write the class for the other type ourselves. The difference is we have to write a class only once, and we can instantiate it with as many types as we like, as long as they're compatible to the interface. So this is the major thing about templates, at least for me, among other things. Templates, it's probably more understandable in English anyway. When I give German training classes, I have to explain this a little bit more, but templates are a kind of pattern for the compiler to fill the blanks in. And here we can instantiate templates with different types of values. So if we only write a template, there's nothing much to do for the compiler, just parsing it. But once we start instantiating it, so using it with a concrete type, then we get a code for it. And each instantiation for a new type or value results in additional code because the template, the blanks are filled in and the compiler generates the code out of it for each argument or each argument combination. This is something we need to be aware of. But as I said, it's the same as if we would write the same code twice or 3 times or more, just that we have to do that. And here the compiler does it for us. So that means templates reduce a lot of writer's work. We do not have to implement the functions multiple times just because they are slightly used with a slightly different type. We have 4 different types of templates. We have function templates, class, and variable templates. And we'll see them all. They always start or are initiated with the keyword template. So this is how you can spot them, at least until C++ 20, or when C++ 20 comes around in your code base, then that changes because we have the auto keyword there, but that's another story. We have 3 different kinds of template parameters, how we can parameterize a template. We have a type parameter. So this is the probably most common one whenever we use a concrete type, like an int, jar, or our custom class or whatever, then the type parameter kicks in. This is by that the most common one. We also have non-type template parameters. These are values, typically sizes like 3, 5, 10 or whatsoever. Until C++ 17, we could only have or we couldn't have floating point types and string literals there are class types. This changes with C++ 20 or changed because the standard is already out. Now we can have also floating point types and classes as non-type template parameters. So that means that we have an instantiated object at this point, which can be parsed as a non-type template parameter. And the third kind of template parameter is the template parameter. There's the single slide at the very end. And it is required if you pass a template as a parameter to another template. So kind of a recursion, but a little bit different. Questions so far from anyone? I don't see the chat. I'm not sure if there's a chat. So
yeah, I'm monitoring the chat. There are no questions. So I think we're good.
All right.
Unless someone chime in, please do.
Perfect. So the template part's applied. So what I told you so far is all in the single piece of code. We have in line number 2 the start of a template because there is the template keyword. And then in the angle brackets we have in A with type name T a type parameter, and in C, or sorry it's B, and in C with size T n a non-type template parameter. Then I decided to make this function const expert because we are looking at a function template here. It returns auto and its name is size, so that's the usual function at this point. And then you see something you can do with templates. It's the only way I know how to do this. The signature you are seeing for this parameter here, it preserves the array. So usually if you're passing an array to a function, it decays to a pointer. You cannot do anything about this other than putting it into a std array. With this syntax you're seeing here, I'm basically saying that this function size takes a const t reference to an array of the size n. And the compiler is able to deduce the type t as well as the size n of the array. And this allows me, if you go down to line number 15, to use size together with the variable buffer, which is an array of jar of size 16, and simply call this function. And it returns me above in line number 7, it returns me n, so simply the size of this, this buffer. And this doesn't decay to a pointer. It always preserves the array, but this is a sidetrack on templates. Here you have a function template with the name size. It takes a type and a non-type parameter. This is the essential part on this slide. Then we have function templates. We already saw one, but here in more detail. Function templates allow us to implement uniform functionality for different types once and let the compiler fill in the blanks. The parameter types and values come with some restrictions. The types itself, as you can see it in line number 1, are either initiated by type name or class. This is there's a very slight difference between type name and class. With the newer standard, it gets less and less, but in some places you can only use type name and in others only class. But that's not a topic of the day. Then the name of the parameter follows. You usually see, at least in my code, that it's then T for the first parameter and U for the second parameter, but you can also see parameters which come with a more meaningful name than T. You are absolutely free. It's like a variable name. And inside of this function, we can then use this T, which was deduced by the compiler, to either create a new instance or object of this type, or use it, as you can see in line number 2, in the function signature to mark the return type. This is T, and the 2 arguments A and B are of type T as well. And what you see here is a min function. I like to point out at this point, the standard library comes with one. Use that one. This here is just for illustration purposes. It tries to figure out which one of the 2 values, A or B, is less than, and returns that one. So I can use this function min now with 2 integers A and B here in line number 9 and 10, and call it and get the result and print it out with the help of a printf. So this is the function template itself. And once I start using it, as in line number 12, I get an instantiation. And instantiation is the term we refer to all the time when the compiler replaces a template with concrete arguments. So either type parameters, non-type parameters, or template parameters. What you see on the right here is in fact the output of C++ Insights. I use another chance to show you the tool itself. It's the same code, but what you see in between in line number 7 and 14, this is an instantiation the compiler creates for us based on us invoking line number 20, because I call min there with an integer. Okay. And then the compiler creates an instantiation, or you can also say specialization if you like. We'll see that later. In line number 9 there, I have an empty template head. It only has the empty angle brackets. And then I see the filled template. It returns int, it takes 2 integers, and we see that it's a specialization with the 2 angle brackets after the function name, and the type provided here is int. So this is what the compiler derives from this template. And if we switch over to C++ Insights, if I manage to click the right thing here. So this is the original example, and if I transform this and increase the font size a little bit, then you can see this here is C++ Insights. You can get it as a command line tool as well. This is the web front end at cppinsights.io. You put your source code in on the left, and you get C++ code out on the right. So it's roughly like Compiler Explorer, but it gives you C++ code. So a little bit different. And here we see now, after this transformation, that in fact it is the same. I get int and int out here. If I would say, well, let's make this floats, or let's say doubles. And then I'm using 2.3 and 1.9, for example. And I make this a float. And if I transform this now, then we will see that I'm getting now the template instantiated for 2 doubles. Okay. Would I use it with 2 integers as well? Let's say we use it in addition with 3 and 4, like the integers we had before. Then we will see that I get 2 instantiations for min or 2 specializations, and both of them do the right thing. Here I have the one for integer, and here I have the one for double. Okay, so this is the brilliancy about the templates, that they generate the code for us. Questions about
Andreas,
this so far? Yes.
Yes, short question. I thought in the previous slide you mentioned that floating point types weren't allowed as template parameters. Maybe I misunderstood that.
They are not allowed as non-type template parameters.
Ah,
Sorry if I was
okay.
precise. These are
No,
template
that's
parameters.
my fault. Okay.
We'll get to that later, but essentially what you cannot say is something like this until C++ or yeah.
Got it. Okay, thank
Before
you.
C++ 20. You're welcome. Other questions?
What is special about this floating float type and string that we could not have before C++ 20?
So what's special about this float that we could not have it in C++ before C++ 20 is a non-type template parameter?
Right.
The representation, if we take this and use the other tool we use all the time, this compiler explorer, and make the font size bigger once again. And if I do run this and I turn demangling off, then now I have to change my example. Let's say this one takes a double. We discard all this. We call this fun, for example. So what I have to do for a non-type template parameter is something like this. I have to provide a number because it's not a type, it's a value. It's a non-type template parameter, so I have a value here. And now I call this function fun, and now I'm at the GCC. That's too old. All right, that GCC does it. And what we can see now in this output is, well, let me use another example. Let's use 0. It's better. Now we can see what the linker has to do for this function template. It's the same as for every function. You may know that it's called name mangling. The compiler mangles the name fun here into a name that's unique because it contains the return type and all the parameters, such that across compilation units, the linker can track that this is the same function that's called. And now you can see that my double here is contributing to all these zeros. Once I would say this is an integer, and it compiles, then you can see that the mangled name gets way shorter. It's just a simple 0. And if I switch back to the double, then we can see that this one gives me all the zeros, while the minus 0.0 gives me a different number. It's the IEEE 754 representation for floating point numbers that the standard uses here typically, or the compiler. And this is how the standard says that the floating points are represented, so that the floating point standard. And previously, years back, longer mangled names mean more memory consumption during linking, probably bigger object files, more processing time. So this was one of the parts which we didn't want to pay for back when C++ was standardized initially, because we simply didn't have the computing power, or didn't want to pay for it, basically. And the other question we struggled for a while is, do we use the floating points as they are defined? So 0.0 is a different value than minus 0.0. If you are in math, then that makes a big difference. For other people, it doesn't really make a difference. It just confuses them. And yeah, this was one question to solve, because this function now is a different function than this one. We can now see that I get two template instantiations for fun. One for the minus 0.0 and one for 0.0. And as I said, if you're in math, that's exactly what you like. If you're outside of math, then it may confuse you. And this was, was also sort for questions and discussions whether we like this or we don't like this. Does this answer your question?
Yes, thanks.
Perfect. Other questions before I go back? All right. So I said that we have these instantiations for compilers, and what C++ Insights shows you is what a compiler does, but it's also a specialization, what C++ shows you technically. Here I have such a specialization. A specialization is a procedure where we provide a different implementation for a concrete type or type combination of a template, maybe a function template or a class template. And the motivation here is I have a function template called equal. This checks two values for equality. And you may notice from your computer science classes or from experience, comparing two floating point numbers to equality is something where you shouldn't use equals or equal here as in line number 4, because maybe they're only in a fraction after 6 digits after the period point where they differ. Depending on your application, this may matter or may not matter. So for double, we can use a specialized version of this equal function where we can say we build the absolute value from a minus b and compare this to some threshold, usually called epsilon, but I used a different number here just to have the number. And now I can call in line number 18 equal with 2 integers, and in line number 23 equal with 2 doubles. And the compiler will call, for the first call, the function template instantiated with int, and it will use my function equal, my specialization, for the second call. And we can see this here in C++ Insights. What I'm getting now is slightly different to what we had before. Once it's transformed, the website is usually faster if you do it yourself, but I'm hosting it on my laptop, and with all the streaming here, it's a little bit too much for my laptop. Now the request failed. That's too bad. Oh, come on. Let's do this online. Let's do it that way. Should work as well. So now here we go. That's faster. So now here we can see this is what the compiler does for us. This is instantiating equal with the type int. And this is what we provided. This is equal for double. And you cannot see this here in the call, but if you would execute it and I don't know, step in with your debugger, you will see that the first one calls the int version and the second one calls the double version. So this is what we can achieve with specializations. This is slightly different to what you can also do to overloading. Just get rid of the template head here in line number 7. Then you have a classical overloaded function. There are slight differences between that, and you can use the overloaded version as well. Here depends where it appears, which one picks it up. The overload is often a little bit the better choice, but you have the ability to specialize things here if you have a special case for something. Questions regarding specializations of function templates so far?
How does the compiler make a choice between the main template and the created specialized template definition?
Good question. So this is happening during overload resolution. The compiler practically, I'm not 100% sure how it goes in this case, but it's roughly that the compiler sees, let's say, the call to double, and then it first checks whether there is a function double or an equal function taking double. And it may try to instantiate our function template. We call this the primary template in line number 2, equal with double. But it later sees that we provided our own version. And now it has, at some point, internally 2 equal functions with the same signature. But the compiler knows the one is a specialization we provided. And the rule of thumb is in C++, if we as users do work, the compiler honors that and says, okay, you did extra work here, I used your function. This is roughly the process that happens if all the arguments are the same. The more specialized we provide our function, the more we win, or this function then gets picked, as opposed to the compiler has to do something by its own. Does this help?
Yeah, thanks.
Perfect. Other questions? So then let's switch from functions to classes. We can also have class templates here. They, to some extent, work like function templates. They can have the same kind of parameter set. If you look at the example on the right, on the top, there's the A and B here. It starts with the template head. It can have a type and non-type parameter, and of course, template parameters. So it's a template, so it gets introduced by template. And most rules of function templates apply for class templates as well. There is something that you don't have with function templates that's unique to class templates. We can have methods in class templates. And there we can once again decide, do we like to get them instantiated based on the class template, or are they a template on their own? So a method template inside a class is possible. And because we have a class, some method here, the example is data in line number 4, can be implemented outside of the class. So out of line is the term in C++ here. While the same function for const in line number 5 data is implemented in the class, or in the struct in this case here. So this is a difference we can make for classes in general. And if you do this and it's a class template, then as you can see in line number 17, I have to repeat the template head. This has to be the exact same template head as for the class itself, because this helps the compiler, or it's the way how the compiler pieces these two together. And then in line number 18, we have to say that this data method here, this data function, this is for array, for the type array, which is a template, and we have to pass along these two parameters of the template t and size, so the type and the non-type template parameter, to make this work. This is one reason why I personally tend to implement all my methods or functions of a class inside of the class, because it's a little bit more to write. And there's another thing I haven't mentioned that's true for methods or for functions. Once it's a template, the compiler must see it when this function or class gets instantiated. So you cannot, for a function, for example, forward declare a function template, or for a class, forward declare class template, and moving the implementation into your CPP file. Once the compiler...
Sorry to break you here.
Sure.
I did encounter this recently. Do you know the reason for this? Because like we'd have to move it to a header file, and the compiler, it's the linker that complains that it's an undefined reference, right?
I'm not sure if it's the linker or the compiler, actually. So let's say, just to be on the same page, let's use Godbolt here for a moment. I cannot emulate this in Godbolt, but say I would have something like this. No, that's not. Let's do it this way. And takes a t, and let's say we instantiate this with int. Yeah, not that way, that way. So let me see whether I can reproduce the error I'm looking for, or which thing gives you. Okay. Now it complains that main is not here. Okay, so then it's probably you're right. It's the linker. I wasn't sure. So the process that happens here, if you forward declare or attempt to forward declare a function template, at some point the compiler needs to instantiate that. But because we just splitted the definition or the declaration on the implementation, the compiler has no reason to instantiate the implementation because it's in a different file. And the linker cannot do this later. Once you manage to use this function template or this class template in the CPP file where the function template or class template is declared, it works, because then the compiler sees the implementation and can instantiate it. But if we split it, I would assume it's a compiler error, because the compiler doesn't know this function, but maybe it's the linker later triggering, and the compiler just generates the forward declared version. So, but this is the reason. The compiler needs to see this function at a point where it instantiates it. If it doesn't, it simply doesn't instantiate it, and later the linker says, hey, I don't have the code you're telling me that should be there for this function or class. This is the reason. Does this answer your question?
I didn't quite get the first part of your reason. Can you expand a little?
The first part, what was the first part? or
Like,
what
can you
refer-
go over the reason again? Like, I didn't catch it right.
The process of instantiating, let's reduce this to only a function template, is when the compiler sees this call here in line number 6, and it has only this forward declared function template. Then at this point, we can see it here. The compiler places a call and says, this function needs to be called at this point. But it doesn't instantiate the code behind it because we haven't provided it here. It's not here. It's somewhere else. We moved it to the CPP file. Let's assume we are looking at a header file here. I cannot simulate this in Godbolt, but assume this is the header file. Then the compiler understands that there is a function fun, which is called with 3, so the compiler can make up this call. But it does not instantiate the function template because that code is somewhere else. Now later, the linker comes and sees that this function needs to be called. And it looks in all the object files and will say, hey, there's a linker error. This function isn't there because the compiler didn't instantiate it. Once I give this thing here a body, for example, then we will see that it appears. And what I'm doing here now in the single file Compile Explorer is basically the same as you will experience if you split it between header and CPP file.
Okay.
Does this make sense?
Yeah. So is the recommendation to have the definition in a header file and include the header file?
Yes, put them both together in the header file and include a header file. That's the usual way to go.
Okay, thanks.
You're welcome. Other questions?
I was just going to add one comment. I've seen, the increase in popularity of header-only libraries, and that's the term that I've seen some open source projects use for this very reason. So it's not that uncommon.
Yes, these header-only libraries you refer to, they have multiple, I think, good parts to it. So it's always easier if you only need a single file as opposed to a couple of files you have to compile yourself. That's one reason. C++ 17 added some things that make it more feasible to have everything in a single header file. I'm referring to inline static there, if you notice. So if you have a static variable inside a class, for example, we always had to initialize it in a CPP file. It couldn't go in the header file. Otherwise, we had duplicate symbols and something like this. So this also contributed to the fact that we now have more abilities to these header-only libraries. The other thing is const expr. Once you have a const expr function, that function gets implicitly marked as inline. So you can also not split it across header and CPP file. And because more and more code is getting made const expr, this is another reason why we end up with all these header-only libraries.
Interesting. Thank you.
You're welcome. Other questions? So for class templates, it's the same as for function templates. Each type you're using this template with creates new code, so creates a new instantiation of this array. What you're looking here at the right is, in fact, the implementation of std_array. This is a very, very clever approach because it uses a struct and the data itself here in line number 14, the array isn't private, it's public. And by that you get the performance we are getting from std_array because it feels like a usual array. The compiler can directly initialize it. We can use the curly braces, the uniform initialization, as we see in line number 25 and 26 to initialize it. without any constructor need. So this is the old term was more or less a plain old data structure. And then we only add functions to it like data, like size, begin and end to access the elements. But this is how std array is implemented basically. And if I use this, or if you look at this in C++ Insights, and I transform this, there you can see I used it with a couple of types here with int and double. And as I told you, here we see an instantiation of int and 2. This is the first one. So C++ Insights also tells you that if it can. So it's from line number 28. Now we see that data returns an int and data returns an int. And I have an array of ints of size 2. And for my double below here, I have the same, just that it's now double and 2. And would I make this, for example, 5, then I will get the same thing, but this time with the non-type template parameter 5, my array size is 5. And of course, if I go back to the original version, more or less, and say this here is size 2, now I'm ending up with 2 arrays of type double, but with different sizes. So size 5, this contains the array of doubles of size 5, and the other instantiation contains a double array of size 2. So this is what we would write ourselves if we do not use templates. Here, the benefit is I have a single piece of code to maintain. If I find a bug here because I did something wrong, I fix it here, and all types I'm using it do profit from this fix or get fixed. So this is the major advantage of templates. Questions about this?
Is there any concern regarding code bloat with templates?
I have a couple of slides regarding this, yes. You should keep it in mind, but we will see later. Good question.
By the way, I like how you use address of std address of for getting the address of the m data 0 instead of the %. Probably not. Kind of, it's a better if this % is overloaded or something.
Yes. Yeah. Thanks. I try to use the standard library elements in my talks to also show them as long as it allows it. And this is one of the places because yes, if we overload things or something like this, then address of can have its benefits.
Yeah, I like that.
Okay, great. So we already saw this class template instantiations work the same way as function template instantiations. The difference is that a class template cannot automatically derive its arguments. We saw for function template, if I declare the simple function fun I had with a single type parameter t, then I can simply call fun and pass 3, for example, and it will work. This doesn't work that much for class templates. Here we must specifically name each argument. We saw this with my array example, or we can see it here. There in line number 25, I say array of int of size 2, and not simply use the praised initialization here. If you use a std array, then this is different. You can use a std array despite the fact that it's a class template without naming the arguments explicitly. And the reason for this is the exception I have on this slide here. Starting with C++ 17, we have a new feature called class template argument deduction, or abbreviated CTAD. And this is a hint for the compiler. If you approach this class template, there is a way how you can figure out basically the arguments, and we can write these so-called deduction guides ourselves. And this is why for std_array or for a bunch of other types in the standard library, we don't have in C++ 17 explicitly name the arguments. We can, for example, create, I'm not sure if you already seen this. Say I do have a stud vector here, and then I simply create such a vector and call it, we initialize it with some values. So this is what you usually do. This is a good thing to do because you are explicit, you say which type this thing is for. And if the compiler makes it, this compiles. Take this to the real Godbolt. Seems my machine is way too busy. Come on. No. Oh, thanks. So yeah, way faster. So it compiles, don't mind the tremendous amount of code. And in C++ 17, if I say here C++ 17, then this compiles. Once I say C++ 14, this doesn't compile, and the compiler tells us that it doesn't know how, or it doesn't know type vector, because there is no argument list for that thing. So here I need the int in C++ 14 and before, but with C++ 17 we have this CTAD, and there are deduction guides for std_vector and for all the other containers in the standard library, allowing us to do this. Okay, so in some cases this is really neat. In others it's maybe distracting because you don't know what's the actual type. I already said this, or with a sentence, in class templates we have the possibility to make members templates as well. The example here on the right presents a class foo. It has a constructor, and then in line number 8, or more specifically 9, it has the operator or the assignment operator or equals operator. And this is a function template here within a class template. Foo itself in line number 1 is a class template, and then in line number 9, or more specifically 8, I'm making the assignment operator a function template as well. And this can be very handy. The example below in line number 21 is I'm creating foo of type int, and I initialize it fi with 3. And now I can, thanks to my method template here, I can assign 2.5 to f of I. And internally in this assignment operator implementation in line number 11, I use a simple static cast to cast from anything that's castable to or from whatever it is to an integer. I'm doing this cast here. I'm assigning this to the internal value of foo, and then I return a reference to this instantiation or this instance of the class. Probably don't do this at home. It's probably not so wise. This example I'm having here, I'm automatically converting a double into an integer. But you can put more beef into this assignment operator function and figuring out whether it's the right type you'd like to convert from. And it's okay if you round down or round up whatsoever. But they enable us to do even more things that are very handy with classes. You don't necessarily need a class template to do this. You can have a regular class, which is not a template, and template certain operators or methods, whatever you like in there. The only exception is that the copy constructor and the destructor, they cannot be templates. This is especially the copy constructor is often a source of error. So here in line number 4, this isn't a copy constructor, this is a conversion constructor. Because, no, sorry, this is okay, this is a usual constructor. But once you try to make it a method template again, to catch more types, it stops being a copy constructor and it becomes a conversion constructor, because basically it takes every type and converts it if convertible. So the constructor, the destructor and the copy constructor, they cannot be templates. And for method templates, it's the same as before. We can implement them inside or outside of the class. If we choose to do it outside of the class, we have not only to repeat the template head of the class, but also the template head of the method we are referring to. So it gets even more code if we put it outside of the class. And there's another special thing that comes with inheritance. So the example on the right here presents a class template foo, which has a function func. Don't mind the implementation, doesn't matter. It's just empty for the sake of illustration. And then in line number 8, I define a second class template called bar, which publicly derives from foo and uses its own type parameter t to pass this to foo, to instantiate a foo object, because it's a class template, so it needs its arguments. And then in line number 10, I have this function bar func, and it tries to call func from the base class, because foo is our base class, foo has a function func. And line number 12 sadly doesn't compile. That's why it's in a comment here. The compiler tells us that bar doesn't have a function func. So this is one case where you specifically have to say this error func in line number 13 to tell the compiler that func is part of this class. Or the alternative is to say foo in angle brackets t to refer to the base class : func to say specifically I like to call this function func in my base class. Because my base class is a template, I have to say which type this base class is of, so foo of t. So this is a special case. If you approach something like this and it doesn't compile, then it's most likely because you've written the code as you usually do, as in line number 12, without prefixing it with this, or specifically referring to the base class. But then you have the choices in line number 13 and 14 to say specifically that you like to call this function from the base class. This is a specialty about functions.
I didn't get it. What is the difference between 12 and 13? Because 12 is supposedly to be working it same as 13. Why? Why you have to differentiate it?
Why I'm differentiating 13 and 14?
Why 12 will not compile basically?
Because we are in a template here and the compiler simply doesn't understand that we are trying to refer to func from the base class, because the base class is a class template and we need a type, and the compiler isn't allowed to, at least, to behind our back say, oh yeah, that's func from foo of int. So let me try it this way. Let's use code for this. And take a sip. So this is the example from the slide. I take the coloring off. Better. So once I try to compile this with the usual way, the compiler says I have an undeclared identifier func. Now imagine I'm not limited to derive from my foo here only once. I could also say I call another one which is called foo of char. And then the second one stops compiling here, my second choice. Only this one remains, because now I have the option, basically, because I'm instantiating this with an integer here below, to say I like to call the function func from foo of int or the function func from foo of char, because these are different functions, these are different classes. And this is the reason why this can never work, because the compiler doesn't know what this func is. Why does it work now?
I see. Yeah, thank you.
Now it works because I specifically named it of char. So now it calls basically func of char. C++ Insights is probably able to tell us this. No, sadly not. Okay. All right. If that's clear, then it's perfect. Other questions regarding this? As I said, this is a common trap where you may run in.
What happens when we are overriding?
This function isn't marked for overriding, so let's say I make this virtual to make it correct. And if I now say something like this, you're asking for?
Yes.
Doesn't do anything like in the base class, but it's a different one. Now this one gets picked, because now there is a function in the scope. Okay, now you change the rules. It starts probably getting different if we do something like this. And now even I have no idea which func gets called or which func gets overwritten. I don't know. But my bet is probably not the one I like to. Yeah, sadly, maybe we see it here. Okay, it says this func, so it calls. Yeah, it doesn't matter. Okay, because I'm overriding it. Because I now specifically override the function func in the base class, it doesn't matter of which base class I'm overriding func, so it always calls this function.
Mm-hmm. Okay.
But this is probably now more advanced than I intended to go, so I don't like to confuse you. If we do this, yeah, now we see it's derived. And once we stop doing this and say we like this version, then we see foo here. Okay. Other questions? All right. Then what else can we have? We can have alias templates. We can have a using alias like we see it here. in line number 4, and we can put a template head on top of it in line number 3. And there we can now say, for example, that I have a char array. This is an alias for a std array of size n. And in code in line number 8 later, I can use it and can say I like a char array of size 24. And behind this, the compiler instantiates or creates an object of std array of type jar of size 24. And this is handy if, for example, you have the case that you compile your product, your code, with different libraries for different customers. So one likes to have its own array type, the other one has the STL, the next one has a Qt array or something like this. And assume they're all compatible in their interface or you only use the compatible parts. Then you can, instead of sprinkling this all over your code base or using ugly defines, now say you're using an alias template, say it's a char array as before, line number 3 and 4, and then sorry, I have to use if def here. And then you can say, okay, if it's product A, then use this array of type char of size n, or if it's not product A, use a std array of type char of size n. And then the code in all the using places, you simply say, as in line number 13, it's a char array of size 24. So you don't have to care for the actual type. So you can put a bit of an abstraction in here. This is a good use for alias templates if you have such a case. Or if you like to hide a template parameter, like in char array, because you gave that thing a name and it's not necessary to repeat std array of type char all over the place, then that's another way to hide template parameters, which are defaulted if you like. Questions to alias templates? Then let's circle back to the question we had earlier. How efficient are templates? So here are a couple of guidelines, or one guideline for efficient use of templates. Templates generate code for us. It is if we would copy and paste our implementation and only change the types or the values. Okay, it's the very same. The only difference is if the compiler does it in a template, it never diverges. It's not that last week I copied from this source, now I'm copying from another source, and it's both time the same function, but once was modified and the other one wasn't. Depending on the compiler and the optimizer, the process of instantiating templates can result in a larger binary. Most likely the reason for this is because you're using your template, your class template, your function template, with more type or non-type template parameter combinations than you are aware of. Maybe in a world without templates, when you created the multiple functions yourself, implicit conversions would have kicked in and reduced your correctness of your program, maybe, or the precision of the numbers, and it simply have worked. Maybe that's all right. But due to the implicit conversions, you only have, say, 3 functions. If you use function templates, then you get guaranteed an instantiation for each type you're using it with. Say you're doing this with 5 different types, then you're getting 5 instantiations of this function func. So this is more code, but the code is more correct. Depending on how good the compiler and optimizer are, and these days they are very good, they're able to figure out that there are great similarities between these implementations and reduce differences and give you even better binary maybe. Sometimes we overlook this fact that we told the compiler to instantiate this template with 5 different types, which is the reason why we get 5 different copies of it with 5 different types. And once we overlook this, this is often what people refer to as code bloat, because then people say, hey, earlier I only had 3 versions of this function when I copied it on my own, and now the compiler gives me 5. But the reason is you're getting better code, essentially. So this is one thing. The other thing is this code bloat thing is in our control. Let's have an example. Say we have a typical C API, which is horrible error prone. I have the two functions send and read. Send takes a const jar data and a size t. Read takes a jar pointer data and a size t. What does send do internally? It checks whether data is a null pointer. If not, it calls the POSIX version of write, forwarding, size, and data. And read does something similar, just that it reads to our buffer. Now in main, I created two buffers, buffer 1 and buffer 2, or buffer and buffer 2, and line number 17 and 22. And then I call subsequently read and send with both buffers. I personally dislike this approach very, very much because I absolutely try to reduce size offs in my code. They're a source for errors. They're ugly to read, ugly to write. Does anyone spot an error with this example?
The buffer 2 needs to be used in the 24-25.
Correct. So I accidentally, let's say, messed it up. Line number 24 does a classical mistake. It passes buffer to read, but the size of buffer 2. Buffer is of size 1024, buffer 2 is of size 2048, twice the big. So I'm getting a buffer overflow here if I'm reading to this buffer because I'm signaling the function I'm using here that the buffer is twice as big as it really is. So this is a problem. And we can try to address this. We can say, okay, we have this cool std array type in our standard library. So let's parse a std array, or let send and read use a std array instead of the jar and lengths we had before. This is a great start. Now I have in one type the data and the size, and I can query the size from this type, and I can query the data from this type by calling data.data or data.size in line number 3. That's good. Now in line number 13, I'm creating a char array, std array of type char of size 24. I'm calling read and send. That works perfect. And then in line number 18, I'm creating another std array of type char and size 2048. And now line 20 and 21 stop working, because my functions send and read specifically say they take a std array of type char of size 1024. And 2048 is obviously different. So that doesn't compile because we are strongly typed in C++. One way out is to say, okay, let's make send and read a function template. Let a compiler that uses the size that's needed for this std array. There's another application you can do with templates. The compiler is able to figure out the size. Now in line number 15, I'm creating the std array as before. I do the same thing in line number 20. And now line number 22 and 23 do compile as well. But what I'm getting now is 2 instantiations of send and 2 instantiations of read. One taking a std array of type char of size 1024, and one taking a std array of type char with size 2048. This is twice what I had before. So this is where we start saying this is code bloat. In this specific example here, so a single line, you do not need to worry about this. The compiler and the optimizers are very smart. They will inline this call and optimize it away. But imagine there is more code in your send function or your read function, then it starts to matter. So the journey started with improving this old error-prone C API, and so far we can improve it, but it doesn't seem quite right because we are risking that our binary gets bigger. We can do a trick. Let me introduce you to StudSpan. StudSpan is a type that comes with C++20, but you can implement it in roughly 40 to 60 lines of code, or you can head over to GitHub. Folks have their versions back to C++98. A span internally stores a pointer and a size. These are the two things a span stores. And the type of this pointer we specify here in line number 1, because span is a class template, there we say jar. So the internal type of this span is of type jar. But the size is simply of size t and deduced at either compile time, if it's a const export context, or at runtime. And the span can be created from a stud array, from a jar array, from various different other things. So it's just a span, it's just a few onto this memory. And now I can write my function send and read as regular functions. No template required, but I use a template type in it with span, or a class template with StudSpan here. Both times of type jar. Now the code that calls it is the same as before with my stud array version. In fact, I'm showing you in line number 18, I'm declaring a stud array as before. I'm calling read and send, that works. And in line 23, I'm creating a jar array as I did before, and I'm calling read and send, and it works. It's a StudSpan. But I get only a single send function and a single read function. And the reason for this is that I did think about it and concluded that this version gives me for every n a new function send or a new function read. And instead of letting this n, the size, be there at compile time or use it at compile time in the function template or class template here, I decided to deduce or determine the size of this array as a combination between run and compile time, and store it as a runtime value in the span. This is depending how you're using it, maybe a little runtime difference, but not to the version as we've seen it before. And I only type the span with jar. So I can create an arbitrary amount of different sized jar spans. I will only get a single instantiation of this one span class template. Okay. Questions regarding this example so far?
So I have a quick question. I remember in C++ 11, there was a new keyword associated to template that you could use, which is extern, and I think it had at least a couple of usage. One was you could reduce the compile time itself, because you would say to the compiler, look, this is instantiated somewhere else. Let's say you have a vector of int, say, don't worry about it, don't instantiate. The linker would find in a different .o, and I think it was always kind of resolving some issues where the compiler would create this instantiation in every compilation unit, and the linker was not that good to kind of eliminate that. So extern was I don't know how well compilers are doing today with eliminating. Let's say I have vector int in one compilation unit and another one in another. Eventually, I don't want duplicate. And let's say things are not inlined. So there's actually code. There's actually definition in a separate. So I don't know how well linkers or compilers are actually removing the duplicated one. I actually not using extern. I'm not kind of timing my or measuring my compile time yet, but I I believe that if I see something that is taking too long because of instantiation, I probably need to use extern.
Yes, I think you described it very well. So the idea of extern is that if you have multiple compilation units and you use your std vector of int in all of them, then without extern, the compiler instantiates this std vector of int in each compilation unit. That means time, because it gets instantiated. It means memory, as well as probably for some time in the RAM, as later on your disk, because the object file contains, or all object files contain an instantiation of std vector of int. With extern, you can do exactly what you described. You can tell the compiler, yes, you will find this instantiation later, guaranteed, I promise. And it doesn't have to worry about it. So you save space and time there. I think compilers were, at least for a very long time, smart enough to figure out that 3 std vector of ints in 3 different compilation units are the same. Basically, they have to. So I wouldn't worry about your binary getting bigger without extern. That is not a case, but you can save compile time and memory usage during compile time.
Yeah, that's what I thought. Yeah, thank you for confirming.
Yeah, perfect. So then let me introduce you to span here. The internals of span, just that you have seen them. Maybe if we had more time, I would be more confident that you're now able to read and understand what you're seeing here. But this is a class template called span, as you can see in line number 1, as we had it. It has a default constructor. There's a constructor for from its pointer type and the size, so from length or from a buffer and the length to be created. It has in line number 9 this special version where it can be created from an array. So there it directly deduces the size of the array, which is in fact what we saw on the previous slide. And it has this for const and not const and for std array. And then you have simply the methods size, data, or empty, begin and end, and you're done. So 30 lines of code. And you're done, as I said. So consider span, especially if you're moving binary data or something like this along. This is very, very efficient because there are no memory allocations, but it's only a few, so the data has to live longer than the span does. So for class templates, what's the guideline? Basically the same as for function templates. Move the code which stays the same for all instantiations or across all instantiations into a base class, in a non-templated base class, because that one is then the same for all of these templates, and it does, it exists only once by the others as a regular base class does. And then wait if storing an additional type of value is better than passing it as a template parameter. We saw this with span. We can use a std array. There we have both parameters at compile time, and with span, by moving the size to runtime, we save a lot of memory, if you like, in our binary. And the guidelines for function templates is check if you can use them as API only and forward the actual work to a non-template function. So this is roughly what send does. Send is for end users. It takes a guaranteed span. There I have the size and the pointer to the data. Nobody has to call size off. That's pretty in the code. But low level, at some point when I call write the POSIX version, I may need to unpack them and pass the pointer and its size once again. So I often use this pattern, so then it's a very small template to make it easier for users, get rid of the size of, and then beneath it in the template, I simply forward to another function, which may be taking exactly what we saw before, pointer and the size. Questions about this? So then I mentioned with templates, we need to sync in types. We usually sync in values, but types are there at compile time. Values often only there at runtime. But types, the compiler need to know at compile time. And one example is the one on the right. This is what you can see in the type traits header, or what sometimes is referred to as template meta programming. I define here in line number 2 a class template, a struct called integral constant. It takes a class T, so a type name T, and then it uses this exact same T to define a non-type template parameter. So this takes a template and a non-type template parameter. And in line number 4, it has with static const expert T an entry value, a member value, which gets initialized with the previously passed non-type template parameter. By that, I can now use alias templates, can use an alias with this integral constant. Say I have a true type and the false type, and I type here integral constant of type bool, true and false. Now I have these two. And then I can say in line number 12, I have a thing that's called isPointer. It's a class template once again, and I say this takes a single template parameter and it derives from false type. And if now I use specialization in line number 16, I say there is a special case of this class template for a pointer type. In line number 17, I'm saying isPointer in the angle brackets T star. And this one derives from true type. Okay, I have two symbols called isPointer. They are function templates, and I have a specialization for it. One returns false type or derives from false type. The other one derives from true type. And then the static assert in line number 20 and 21, I can now say isPointer of e star colon value, because isPointer is a function template, and my value, as you see it in line number 4, is a static member of this structure here. I can call colon value, and this will return me true or false, depending whether the specialization kicks in or is chosen. Line number 17, then it's true, or line number 13, the primary template is used, then it's false. And the specialization kicks in for pointers. So in line number 20, this returns true, and in line number 21, you can see the static assert starts with not. So isPointer of int colon value yields false. So I have to negate this to make the static assert compile. This is how we can figure out at compile time whether a type, for example, here is a pointer or is not. And we can use this to say, okay, we like to limit our std array we saw previously to work only with things that are not pointers. Now I can say in line number 4, static assert not std isPointer T colon value. If I try to use in line number 23 my std or my array with type int star, comma 2, this will no longer compile. The static assert will trigger, will tell me, hey, T here is a pointer, so I don't compile this. Line number 24, where I pass in a regular int, that still works. And this is how we can, at compile time, prevent errors, prevent mistakes, because maybe we're saying, okay, this std array, that should not be for pointers. It's only for types, not for pointers. And a small peek preview into C++20, there we have concepts, and we can change this and can now say in line number 3 that my array requires that T is not a pointer type. And there you can also see that isPointer is part of the standard library, so you don't have to write this yourself. This was just for illustration earlier. But this is the much nicer syntax in C++20. Questions regarding this?
Would there be an alternative? I know we're focused on templates right now, but I'm wondering if would there have been an alternative approach doing this with runtime type identification, or is this just much more efficient?
Good question. Okay, so what's the difference between doing it as, let's say here versus static assert or at runtime with RTTI? Once you are doing this at runtime and you are saying this isn't allowed, well, you have to throw an exception or handle this error in any way. You have to handle it. If you shift it to compile time, then this will simply not compile. And you have to worry about this at compile time before it passes any test or before it fails any test, before it reaches the customer. Here you have the first barrier. And I always like things failing at compile time as opposed to failing at runtime. Whatever I can make fail at compile time, I try to do. So depending on your application, runtime is the better because you say you switch during runtime. So if this isn't possible, then I used another one. Then runtime may be okay. But here we have all the information because we are basing it on the types. There is no need to shift this to runtime and then let the program crash because I try to create array with a pointer type.
Makes sense. Thank you.
Okay, perfect. Other questions?
I don't have a question, but I have one anecdote. I'm using it a lot, static assert and the type traits in my template classes or functions and all. One thing that I found kind of hard to do, and maybe someone has some ideas, maybe offline, how to G-test or unit test these assertions, because it's a compile time error, and most of the frameworks that test your code, they are basically a runtime. I don't have I Googled for that, and I kind of something distracted me, so I didn't kind of continued. But this is one of the things that is still on my plate to kind of figure out.
There is a talk from, I don't recall the name, German fellow at CPPCon, one of the early CPPCons, and I think the title is How to Test a Static Assert. Maybe this is something you can have a look at. It's a while back since I saw it, but it deals, I think, with the same problem. And I personally have a special way how to use CMake such that it understands that this compile failed something like this, but this obviously works only for single static assert, and this is horrible anyway.
Okay, thanks. I'll take a look at
You're
that.
welcome.
Thank you.
Okay, then we have something else that's called the constexpr-if, and it's written if constexpr. So you're starting getting an expert if you can say it and can write it the other way around. In line number 5, you see if constexpr as opposed to naming it constexpr-if. And this is an extension for constexpr. And the guarantee you get there is that only one of the branches survives compile time. In your binary, you will end up with only one of these branches chosen. And the pattern here is the same. Because we are looking at types or compile time values, it doesn't have necessarily to be types, we can choose here what we want. And the function I'm having here is get value. It's a function template, it takes a t. And what I'm doing here, I use this constexpr-if. I say, hey, if t is a pointer, then I do an assert whether t is a null pointer. And if it's not a null pointer in line number 7, I dereference t and return the value. If t isn't a pointer, then I can directly in line number 9 return t. And this allows me to place different calls to get value. Here in line number 15 and 16, I'm creating an int I, an int star IP. And now I can call getValue on my integer, on my pointer to an integer, or simply with an integer, and I will all the time get the value back. And if it's a pointer, I get the static assert check. And if it isn't a pointer, then simply nothing is to be done there, and I get no assert because it's not a pointer, nothing to assert. And if you look at this in C++ insights, then we can see the instantiation of getValue for int. That leaves me only this, my if branch that's still here, but the compiler throws this away in a later stage, but it is empty. It doesn't have the assert or the return. Only the else branch has the return. And if I look at the int pointer, then here you see the expansion of the assert in the internal implementation here, and the dereferentiation of t, and the else branch is gone. So this is very effective to have one function and let it decide at compile time what should be done. This is different to overloading this function. Both have their benefits. I often like it if the functionality is only in one function and I don't need the overload. So this is one way to go down. And you can do very handy things with that. You can, for example, have a function template called str or string, and you can pass anything to it you like. And with the context per if, it checks whether this t, this template parameter t, is convertible to a std string. If so, I simply in line number 5 return t, because by returning it, the compiler will automatically convert it into a std string. And if it's not convertible to a std string, then in line number 7, I call toString to convert my t with the help of toString into a std string object and return that. And this allows me in line number 13, for example, to call str with the string 42, or in line number 14 with an integer 42. And both times I'm getting back a std string. And I have this all in one function. As I said, you can also create overloads to it, but imagine you have more things that need to be converted, then this is very nice. Questions regarding the context per if?
Does that mean that if you have something like inside the if context per, and you have two sections, the if part and the else part, and there's a situation that the if part does not compile at all. So if you have, for example, an invalid code in the if part, and how do you call it? I want to compare it with the macros that we have, the if def. Is it does it work like exactly like if defs or not?
Very good question. So depending on what you like, I would say it works better than the if def, because the code in there must be valid. It must be parsable. And I see this as a benefit because in the macros, or the if-def version where you if-def out something, I often see in that code rots in there and gets messy because it's never used, but it's there. And then a month later, somebody flips this if-def and the other part kicks in and it doesn't compile and nobody understands why. So here you all the time have the entire code. It must be parsable. It must be valid. This is the plus, as I think. So directly to answering your question, say in line number 5, I would forget or have removed the semicolon. That thing would not compile, regardless whether I'm putting something in that triggers the if or the else branch. Those branches or all branches have to be valid. Does this answer your question?
Yeah, that's exactly what I'm asking for. Thanks.
Perfect. So then let's see. We also have variadic templates. And variadic templates start with a parameter pack. In line number 2 on the right, you see such a parameter pack. And this starts with type name ... or class ... as usual. Can interchange there. And this is a marker for, hey, I'm having a variadic template here. And that means basically that we can pass in an arbitrary number of types. Or if we are looking at non-type template parameters, values. And then my function min below here in line number 7, it uses this parameter pack. So the type TS, that's a parameter pack or a type pack maybe at this point. And I use the same 3 dots, the ellipsis syntax, and say that this function min takes an arbitrary number of additional parameters to A and B. And they're of type TS. And TS can now be anything. It can be 2 ints, it can be an int and a double, depending on what I'm instantiating this template with. And then in C, for example, I can now query how many elements are in this parameter pack with size of ... TS. I'm referring to this parameter pack. It doesn't give you the binary size as size of usually does. Here you get the number of elements in this parameter pack. And this helps me to say, okay, this min function here, it checks whether there are elements in this parameter pack left. If so, it calls itself recursively in line number 13, and it splits up one element from this pack because it passes in M from line number 9, and M already decided whether A or B are less, and it passes in that value together with all the remaining values we passed in. And here in line number 13, then you see the expansion of this parameter pack. When I'm calling this function, I say ts ... And this basically expands you the parameters which are in this pack. And now I can call in line number 19 and 20 my min function with 3, 2, 3, 4, 5. And I can assert that the result is 2. This is the minimum value in this set. And I can call it with 3, 2, and this also compiles. And if you look at this in C++ Insights, and I transform this, then we can see we get here the instantiations as before. And nothing really special is happening here. If you notice thoughts from printf, from variadic functions from C, there all the values are put on the stack. This is why, for example, for printf, we have to say %d to tell printf that's an integer, which is on the stack. And if we are mistaken here, then, well, we are getting a number out or a crash. The 3 dots in a variadic template mean that the compiler expands this at compile time. It's type safe. So here I have my function min with 4 integers. And it takes A and B, the 2 parameters that are always there, and here are the 3 additional ones that are getting passed in to this version of min. And because it calls itself recursively, here I have another instantiation of min taking 3 integers, A and B, and my 2 TSs, the types or the additional 2 parameters. And in the body here, we can also see that the call to min is now M, TS2, TS3, TS4, and then the next version it's M, TS2, TS3. So this is the recursion going on, and below here You have the next call, which is A, B, and TS2. So only 2 values get forwarded to min. That means we are in the end here. And this here is then the final version where only 2 arguments exist. And as you can see, body of the const express is now empty, and I'm returning only the minimum of A and B. And this is how it's done. So these are variadic templates. As I said, the major difference between what you may know from printf is this is compile time. It gets expanded at compile time. It knows the types at compile time. So this is absolutely type safe. It's not fishing something from the stack. It's like we would write it by ourselves, by hand, if we had to. But once again, it's nice that the compiler does this for us and we don't have to worry about this.
So as an immediate use case, I see that we could replace our variadic macros that we use to usually log strings in code, right? So like in terms of like I see this is creating a lot of functions, but that would be inline replacements, right? So in terms of code bloat, this is a lot more code, right?
This can have a tendency to create you more code, yes. This is where you have to decide whether you want type safety and it's worth to have the code, or you don't need a type safety and it's okay to have one of these macros that doesn't know about its types and just does its job. That may be good as well.
Okay, thanks.
Yeah,
You're welcome.
in this example, I bet if we put it in Godbolt, you'll see it's all folded and there's gonna be a single assembly line or maybe a couple of them. I think that one of the problems here is the compile time, because there's a recursive happens, and as long as we don't exceed the compiler config recursive templates, we're good, because you can crash it. But definitely there are some scenarios of everything needs to be checked, but there are scenarios that, yeah, these macros that you mentioned can be replaced.
Okay, so you know the
Got it.
macros
Thanks.
he's talking about. All right. Yes, in this example, we will not see anything because with the static assert, it's used solely at compile time. This is, yeah, another benefit, but everything else is true. It can increase your binary size, but as I said, compilers are smart. It's marked inline anyway, so you have a good chance that code is okay at least. Plus, you get the type safety. That's a really valuable thing to have. Other questions? So then, what can we do with this variadic templates? Here's one use case. Say I have a function, or I like to have a function that concatenates several types which are representable as a string to a single stud string. So this is in line number 17 below here. I have a function called Sturcat, which is a variadic template. It takes a const t reference and then a const t reference to a variadic pack. And internally in line number 19, it first starts declaring the returned stud string ret, and it initializes it with a call to normalize. And normalize, you see at the top here, it comes in different versions. So starting at line number 2, it's there for stud string, for q string, for const char t. There's an overload for a tref then, and every of these normalized functions knows how to convert to a stud string. So the easiest one is the version that already gets a stud string that hasn't anything to do. You can do it a little bit better here by returning a reference because you already have the stud string. The q string calls to stud string. The char t says, okay, let me create a std string out of this char t for you, or of this char pointer. The normalize function taking a tref, so that's all the other cases. There we say, okay, we call toString on this type, because toString will know how to convert, for example, an integer or double to a std string. And then in line number 21, after I called the initial normalize, I say I call a different version of Sturcat that didn't have more space. Usually I would put this in the namespace details or private, something like this. And there I call this underline Sturcat function, passing my return buffer, my return string, and I'm forwarding the arguments. And don't using std forward or std move here because they are references anyway. And then in line number 9, we are seeing this underline Sturcat function, which once again is a variadic template. It takes the result buffer and all the arguments. Here I do this trick I've shown you before. I split up one, oh no, here at this point I don't split. I have my tref and then the arguments. And now in line number 11, I call red plus equals normalize for targ. This is the argument that's always there. And then I'm using const_if together with sizeof for the parameter pack, and I check if there are arguments on this parameter pack. If so, I recursively call underline Sturcat, and I'm passing the buffer and the arguments. And if there are no more arguments, I have all processed all the parameters I had, and all are converted to a string now. And then in line number 23, I can happily return a string out of all the different values. If you're really interested in such a function, have a look at Google's AppSile library. They provide a Sturcat version, which is quite more sophisticated than what I'm showing you here. This is just for the illustration of what variadic templates can bring you. Do you have?
I think this code can be improved by normalize all these different string representations into a string view, and the whole code doesn't need to make any change, but it's much faster.
Your string view doesn't work with a Qt string.
What is? I don't know Q string. So is it like
it's from the Qt library.
Is it like a Unicode 16 kind of thing?
Yes, more or less.
Okay, then it doesn't work there.
You're right. Basically, I agree with you. If you have the chance to use a std string here, that's good. I try to illustrate here if I have types which don't work with a string view. Okay, this is the Q string here in line number 3. Or in general, how variadic templates can help you in your code. But you are absolutely right. String view is a very great utility you should use in C++ 17. Other questions, comments? None so far? All right.
Well, yeah. Just a question. It's a little off topic, but just in my experience with using templates, the hardest thing to get used to is the very long error messages. I was just wondering if you knew of a utility that would try to reformat the messages that come out from the compiler to make them more readable. Seems like there should be, but just wondering.
I'm trying to, but I think it was in a different area. So my answer is no, but it's possible that I have heard of something I'm not recalling, or I'm mixing up or forgetting. But no, from the top of my head, I cannot tell you any tool that helps you with that. And yes,
there,
it's
there is something from Vittorio. I'm trying to. It's from my memory. You know Vittorio, right?
Romero.
Andreas.
Yeah.
Well, he had something in his GitHub for templates, parsing templates. I'll need to look it up in his GitHub. I'll paste the GitHub, so if someone wants to kind of look at it. There was something that he, like a script that takes it and makes it much more fun to read. I just can't remember the repository name itself. He has 169, so it's a lot.
Okay.
But there was something. Oh, here, found it. Yeah, so Camomila. I don't know if I pronounce it correctly. I haven't tried it. I just bumped into it like some time back, and so take a look at that. So you just take the
oh, that's great.
output.
Yeah, I definitely will.
Yeah, yeah, yeah. If you find it useful, please let us know. I know about it, but I haven't tried it out. So
Okay, I will. Thanks, Kobe.
It is probably the same thing I had in mind. Yeah, thanks. Perfect. All right.
I just look into a QStream. It seems if it doesn't convert to stream view, just leave line 3 intact, but modify line 2 and 4 to return stream view, and then the whole thing still works.
Yes. As I said, I was trying to illustrate a different point. But yes, you're right. You can use string for these two. All right. Other questions? Good. If there are no more questions, I had quite fun speaking here today. I hope you had too, and could share something useful for you for your day-to-day basis. This is a little bit far-fetched, but if you're interested in C++ 20s and concepts, I created a concept cheat sheet here. You can get it with my other domain, fertig.io/subscribe. It will directly lead you to a newsletter where you can sign up and you get the cheat sheet as PDF. And now I'm seeing a hand up from Moe. Is it right?
Yeah, I have a question. How does this non-type float parameters for templates works on the cross compiler situation? How do you handle that? Because we have some similar situation with the static const float in a class, and we cannot use that because of the cross compiler situation. Does that apply to these templates parameters?
I'm not sure. My initial response before you added your last part was it doesn't matter, because if you're cross-compiling, the compiler obviously needs to understand your target architecture and needs to generate code for it. So for the template case, like I've showed it to you, the compiler needs to understand what floating point standard the target architecture uses and use that one anyway for all the other floats as well. So what problem did you experience?
I haven't used on templates, but because I know that for static const flows in a class, we cannot initialize it in a class, right? In the same line that we are declaring the variable. So I was thinking that when you are using it in the template, or like a floating value, and that template is trying to generate a function name out of that float value or double, what if we compile another? I'm not sure if it works or if it is the same or not. But if we are using a compiled object file from one compiler, and we want to link it to another object file from another compiler. Do they have like the same name function? They generate the same name for that function or not? I'm not sure though.
Okay, now I'm getting it. So by cross-compiling, you're saying you're compiling things with different compilers, but not you're compiling on Windows for, say, ARM.
Yeah.
You're you're compiling one source file with GCC and another one with Clang, and then you're trying to link them together with
Right,
each
something
one
like
of
that.
the. Okay, so if you do this, then they both, I think, use the Ethereum API. So you have some guarantees that it works, and I think most of the time it works. So as an example, Clang uses the glibc under Linux to work. So there's obviously a possibility to do this. But you're right. Maybe they do things different. They would be allowed to, depending on what their internals say. The standard doesn't specify that two compilers have to do this, to bring the same object file. The standard doesn't talk about object files and then how they should look like.
Okay, thanks.
You're welcome. Other questions? Final questions? All right. If not, then as I said, I'm glad that you invited me here. And at this point, I am fertig. Thank you.
Thank you. Andreas, this
Thank you
is
so much.
great. Thank you so much.
Thank you.
Huge
welcome.
topic.
Thank you.
You did a great job. It's very hard to get templates. Even in 2 days, 2 hours is like amazing. Thank you so much. I really enjoyed.
You're welcome. Enjoy your Saturday or your weekend.
Thank you.
And hopefully see you at the CPPCon or something like this. Not this year, probably, but next year.
Thanks.
Thank you, Andreas.
Thank you.
You're welcome.
Thank you.
Thank you, everyone.
Bye-bye.
Thank you.
Thank you.
You're welcome. Bye-bye.